Hi everyone, Happy New Year and welcome to this first LimitState webinar of 2025. I'm Tom Pritchard and I'm going to be talking to you today about streamlining the assessment of masonry arch bridges to CS454 and CIRIA C800 using LimitState Ring. Before we get going, a little housekeeping. So the webinar is set to last about 30 minutes in total with some time at the end for questions. You can post those at any time using the interface that should be in front of you. But as time is quite limited and there's a lot of people here today, we might not have time to get around to answer all the questions. We do aim to follow up on any that remain unanswered at the end after the event. If we have your email address, then we'll send you an email reply, but sometimes the questions do come through as being anonymous. And in that situation, as long as it's appropriate to do so, what we'll do is we'll add an answer onto the end of the recording of the webinar, and then we'll make that available in the next few days. If anyone does have any questions about what they've seen here today, outside of the webinar, then we're happy to take them at info@limitstate.com, and I'll repeat that email address again at the end of the webinar. So without further ado, I think we need to dive into it. So I'll just turn off my video and we'll get going. So an overview of what's going to be happening today. So we'll have a very brief introduction for those of you who maybe aren't familiar with LimitState Ring. We'll then take a look at CS454 and CIRIA C800 through the eyes of an engineer who wishes to assess a masonry arch bridge. After that, I'll outline a few of the practical features within LimitState Ring that allow engineers such as yourselves to use the software to quickly set up and solve a CS454 or a CIRIA C800 problem. Then we'll use the software to do just that. We'll look at a bridge that we create from scratch using a template file, and secondly, a quick look at interpreting the results of the permissible limit state analysis using LimitState Ring. And then finally, I'll wrap up and open the floor to take a few of your questions in the remaining time. So first off, a quick introduction. So masonry arch bridges are durable and quite crucial components of our transport infrastructure, but they do face ongoing challenges due to the combined effects of both the aging process and modern transport demands. You can see a few examples here. Many of the bridges are carrying heavy loads, and many of them contain unique details that can affect their load carrying capacity. What is Ring? For those of you again who don't know, it's an interactive software tool that allows us to analyze masonry arch bridges, and it's capable of modeling, amongst a lot of other things, single and multi-span bridges, a range of potential failure modes, local properties and defects, support movements, and perhaps most importantly for today's session, it will also allow you to analyze the permissible limit state performance. There's not much time in the webinar today to delve into the finer details of all the features of how it works. So if you're interested in those, then we do have a number of YouTube videos, and the user manual is quite comprehensive, and I'll link to a few information sources at the end of the webinar today. So first off, assessment to CS454 and CIRIA C800. On the left here, you can see CIRIA C800, and that provides practical guidance to practitioners who are involved in the assessment of bridges that include masonry arch elements, whether they be highway or railway. It brings together knowledge from existing UK assessment codes and recent research on masonry arch bridge behaviour, and provides useful information for assessing engineers who may have a range of backgrounds and experience levels. So it's definitely something that's worthwhile seeking out if you don't already have a copy. And the guidance introduces the notion of the permissible limit state, which seeks to identify when load-induced degradation may or does occur during a bridge's service life, and we'll be talking about that quite a lot today. And then on the right-hand side here, we have CS454, and that provides detailed requirements for assessing the condition, the capacity, and the safety of UK highway bridges. So more than just masonry arches. But Chapter 7 in particular of CS454 outlines the procedures for structural assessments to ensure that highway masonry arch bridges meet or surpass both safety and performance standards. And that and performance standards is an expansion on the scope of the predecessor codes, which are listed in very small letters at the top there, such as BD21, which only really considered the immediate safety or the collapse or ULS ultimate limit state. So effectively, it's now acknowledging that service load behavior is important, just like CIRIA C800 is doing. Early versions of CS454 dealt with this assessment to prevent distress by using an approach described within the document itself, whereas the newest version, so revision 1.1 from October 2022, additionally allows for this C800 permissible limit state approach to be considered instead. And we'll be taking a look at both of those today. So first off, what is the ULS, the ultimate limit state assessment of masonry arch bridges? Look at the maximum load that a structure can withstand before it collapses. They typically use plastic analysis methods that were first developed in the mid-20th century and have been applied to masonry arches, first off by researchers like Heyman, and more recently, sort of Bill Harvey, Matthew Gilbert have been looking at that. And essentially, the ULS says that safety is ensured if an equilibrium state can be identified without violating applicable yield criteria, which tend to relate to mainly hinge formation and potentially also sliding at contacts and crushing of masonry. And as stated, the ultimate limit state is what we would traditionally be considering when we were assessing a bridge using, for example, BD21 and associated codes. And that brings us on to service load behavior. So in practice, bridge owners rarely observe ultimate limit state failures, which is a very good thing. Vehicle loading, though, in terms of the magnitude and changes of pattern caused by running a wide variety of vehicles around the highway network, can cause a seemingly good masonry arch bridge to degrade quite quickly without necessarily reaching the ultimate limit or the collapse state. So it can be very useful for us to be able to check the behavior under service loading and then maybe before routing unusual traffic over structures of concern. And that can help us head off problems before they occur. So the permissible limit state helps us to identify these cases before the damage is done. And that's taken into account, like we say, in both CIRIA C800 and to all intents and purposes through CS454 as well. So what is the permissible limit state? Excuse me, it's a key feature of CIRIA C800, and it defines that state beyond which long-term degradation of the structure is likely to occur. And establishing the PLS, like we say, is extremely useful for bridge management purposes. We know that the ultimate limit state doesn't really examine day-to-day behavior, just the extreme of the collapse state. So it's useful to understand what the difference between that and the permissible limit state is. And there's two things in particular that we're looking at. Firstly, masonry properties aren't considered in any great detail in the ULS analysis. However, in practice, we know that the properties will start to degrade over time due to things such as environmental effects like scour and brick friability, long-term loading or creep, and especially repeated loading or fatigue. And this needs to be accounted for somehow. We also know that the soil backfill significantly enhances the load capacity of a bridge by adding vertical dead weight to the structure and pre-stressing the masonry, as well as being able to help disperse vehicle axle loads and provide passive horizontal restraint. And these are all considered in an ultimate limit state analysis, as you would do in Ring. However, mobilizing the horizontal passive soil pressures requires large displacements. making it more relevant to an ultimate limit state model than to your normal everyday situations where joint movement and progressive structural degradation through small displacements are more of concern. And like we say, establishing the permissible limit state is potentially a very useful tool for bridge management purposes. So here we have an extract from CS454. Obviously, the whole of CIRIA C800 is written with masonry arch bridges as the subject, but as we alluded to earlier, CS454 looks at all different types of bridges, and section 7 especially is the part that you want to be looking at when you're referring to masonry arch bridge assessment. So at the top here we have clause 7.1, which is relating to the ultimate limit state. And for those who are reasonably long serving in this area, that's what we're used to, determining the ultimate limit state. Clause 7.2 is the one that relates to those service loads. We've used PLS in quotes here, as section 7.2 is effectively trying to achieve the same outcomes from the analysis or the assessment as the PLS in C800. And 7.2.1 here proposes that we assess to avoid further distress by applying, in this case, a fixed factor of 1.2 or 1.8 on the ultimate limit state live load capacity factor, or C, which is equivalent to what we call the adequacy factor in limit state ring. However, in time, it became clear that a one-size-fits-all approach like this, where we're effectively taking a ULS analysis, working out what our factor of safety is there, and just dividing it by a blanket number, is not necessarily the best approach. So the latest revision of CS454 added this ability to adopt the service load approach from C800 instead. Key element for C800 is to carry out two calculations, the PLS and the ULS. I'll go through this slide relatively quickly. It's just to reinforce that the permissible limit state is relying on primary resistance of the bridge. So we're using the self-weight of elements, we're using an endurance masonry strength, and the soil pressures in the spandrels that we're looking at are assuming it's a dense fluid. In contrast, at the ultimate limit state, we're looking at self-weight of elements, but also the peak masonry strength rather than the endurance masonry strength, and also passive soil pressures are now mobilized. We're using retaining wall theory. We know that the lateral earth pressures are typically 1/3 of the peak value. So we're relying on secondary resistance in order to provide the resistance at the ultimate limit state, whereas we're just relying on primary resistance elements at the permissible limit state. One thing to note is that C800 also advocates the use of a multi-level assessment approach, moving from 0, which is like a highly simplified assessment, through to 3, which is an advanced assessment, and each level utilizes different partial factor sets and assumptions. Limit state ring is typically used for a level 2 or an escalated analysis, or maybe a level 1 analysis, which is a simple analysis, and they have similar partial factor sets. Just to say that here you can see an extract from C800 that summarizes the applicable inputs, including the partial factors to be applied in both the ULS and the PLS assessments. Since we're relying on primary modes of resistance in the PLS, the degree of modeling uncertainty is lower than for the ultimate limit state calculations, and that is accounted for in the lower unfavorable action effects for the PLS. So we can see here on the right, these values are typically lower than the ones that we're looking at for the ultimate limit state. However, as we're using endurance masonry strengths rather than peak masonry strengths, and the backfill behavior doesn't include the effects of passive pressures, then you can see that the resistances are modified to account for this in the PLS analysis. So we have a higher value on the masonry strength, and we have K is 1 rather than 0.33 kP for the backfill pressures. So how does that work in practice if we're assessing using ring, for example? As we've seen, CS454 requires you to determine this ULS capacity, and then you can either determine for a PLS in inverted commas calculation that the factor that you get on that is greater than this C min value, and in ring what we'd be doing is using the ULS settings and then dividing our adequacy factor by C min and making sure it's greater than 1. Or if we're using the CIRIA C800 approach, where they're looking at resistance as being greater than the actions on a structure, then we can use the PLS settings and we can look at an adequacy factor being above 1. And we'll look at both of those in a second. Sorry. So next up, we're going to look at the features for simplifying CS454 and C800 analysis using limit state ring. First off, template files. So they predefine partial safety factors and material properties for new bridge models. And in the newer versions of limit state ring, they have a lot of templates for CS454 and C800 built in. Any ring file can be used as a template for a new model. The key values for partial factors, material properties are then extracted and used, and then it leaves the changeable parts such as the geometry and the loading to be specified by the user. And when you come to save the file, it will prompt you for a different name so you don't accidentally save over the original template. With the most recent version, we've increased the number of templates that are available to cover a wider range of the different situations that are possible when considering CS454 and C800 analyses. And the option to use a template file is always presented when you start a new project. And when you're using built-in template files, there's a comprehensive explanation, as we'll see in a second, of the settings and assumptions included in the project description, so you can see exactly what assumptions have been made for your particular analysis. And the second thing is CS454 load vehicles. So generally, when we're undertaking an assessment, we're looking at CS454 table 7.3.1a and b traffic cases. They're all built in to the software. And the library also contains the other vehicles from Chapter 7, as well as cases for lift-off double and triple axle bogies, Appendix B and C vehicles, and special vehicles from CS458. So the whole range of different vehicles that you might want to be looking at are hopefully included, but you can always specify your own as well. So we're going to jump into some examples now. First off, we're going to have a look at using a template to set up a problem and solve and assess to the ULS and the PLS. So first off, I'll start a new project. You can see here that we have the option to use the template. If I open that, then the built-in ones are listed, and we're going to look at the CS454 CIRIA C800 for a good road with normally restricted traffic and a level 2 assessment. So if I open this, we can see here, as mentioned, there's all the information you might want about this particular template in the comments here, but we're going to skip over that and go through the analysis. So I'm going to specify a bridge width of 2,500 millimeters. We'll then move on to the geometry, to explicitly model the left abutments. So we're going to say it's slightly tapered with 3 blocks on the left-hand side. We'll assume just the default span properties for now, but we'll have 2 spans. So we'll have a pier in the middle, which will make 3 meters high. Our second span is going to be just the same as the first, and then the right abutment will make that again the same as the left-hand side, so slightly thinner at the top than it is at the bottom. Next up, we have the fill profile, so we'll make the surface depth slightly lower at 200 millimeters, And then we move on to the partial factors. And that's actually the most important part of this, is that you can see on the left-hand side here, we have partial factors that are associated with the ultimate limit state. And on the right-hand side, we have partial factors that are associated with the permissible limit state calculations. And we can see here that because we've got a good road, normal and restricted traffic, and we're doing a level 2 analysis, then our load factors are set accordingly. And then the material loads and the material strengths are left as unity. When we're doing a permissible limit state analysis, we're worried about the dynamic or impact factors, but we're reducing the axial load and load effects factors, whilst also reducing the masonry strength properties down by a factor of 2. And obviously for the different template files, these values will change according to the type of analysis that we're undertaking. For the materials, again, we'll leave them as the default settings for now. But one thing that's useful to look at is if we go to the backfill advanced tab, we can see here that we have settings for the ultimate limit state and for the permissible limit state. So when we change the type of analysis that we're doing, the way in which the backfill pressures are calculated will change according to the values that are set here. Now, these are set up to be correct for CS454 anyway, so you don't normally need to change them, but it's useful to know that they're there if you need to have a look at them. And then once we've gone through the materials, finally we're on to our loading, and the database here contains a range of load vehicles from different codes and guidelines, like we say, including CS454. So what we're going to do is we're going to select an 11.5 ton single axle from chapter 7 of CS454, and that does tend to be one of the most commonly critical load vehicles that we would consider. And also I'm going to choose, just for something different, a triple axle bogie from chapter 7, a 3 times 8 ton vehicle. And we've brought those into the project. I'll click OK. And now within our scenarios, we can select the different vehicles that we want to consider. In this first instance, I'm just going to consider the 11.5 ton single axle. I'm going to automatically run that vehicle across the bridge from left to right. The final thing that we want to consider is that we can apply a dynamic or impact factor to one or more of the axles. UK codes tend to require you to choose a single axle for the impact factor. And because this is a single axle vehicle, that's pretty easy. So I'll just apply that. And if I click finish, you'll see that our loaded vehicle is here, and it has a red ring around the outside of it to signify that that has the impact factor applied to it. So first off, we're going to do an ultimate limit state analysis. I click play, then you'll see it will set up some of the auto movement load cases. And once that's done, it will start to analyze each of the particular load positions across the bridge and identify the case that is critical. Down in the bottom right-hand corner here, you can see there's also a graph of adequacy factor versus load position. And in the viewer, it's identified the critical loading position for you. We can see here at the bottom left that the minimum ultimate limit state adequacy factor is 1.012. So because we have pre-factored everything, we're just looking for this adequacy factor to be above 1.0 in order to say that the structure is okay in this particular case. What we can do is we can look here in the chart, and anything that's identified with an orange dot is effectively a near critical case. So we can see that actually over the right hand side here is where it's actually critical, but also at some of the positions on the left span, it's almost critical. So you get a good understanding of critical and near critical load positions for this particular scenario. And if I use the slider here to just scale up the movement, we can see we have a 1, 2, 3, 4, 5, 6, 7 hinge failure mechanism that's affecting the entire structure. But now we want to look at what happens when we undertake a permissible limit state analysis, and then that's just a case of switching the drop down there to PLS, clicking solve, and it will run through and do effectively the same thing again using the PLS partial safety factors and the PLS backfill properties for the spandrel zones and over the pier. And we can see here that in this particular case, we've moved from that 7 hinge failure mechanism to a 4 hinge failure mechanism that's only affecting that left hand span. Again, similarly, we can look in the chart and find that there are equally critical locations pretty much over the quarter spans of each of the 2 arches here. But the important thing again is that because the adequacy factor down here is above 1 and everything has been pre-factored, we are assured that the situation in this case is that the bridge is okay under this service loading behavior. So if we look here, we've tabulated the results and we can see our 2 results that we got from that example using the CIRIA C800 approach, both of them above 1, which is good. But interestingly, if you use the CS454 service load approach alone, so effectively dividing the ULS result by a C-min factor of 1.2 in this case, then you can find that in this particular situation, the PLS factor drops below 1 to about 0.93. So by being able to consider the service load behavior in a more nuanced way, CIRIA C800 is suggesting that you're not going to have an issue with the bridge, whereas CS454, using this blanket approach of applying a factor of 1.2 or 1.8 if you've got bad roads, suggests that it is an issue. And this could be the difference between requiring bridge owners to undertake mitigation measures or not. So rerouting, restricting traffic, remediation, example. We go on to the second of our examples. We'll take a quick look at applying the CS454 C800 approach to a real life example of a bridge. So this one's shown some signs of distress under working loads. Have some details here that you might get from a site investigation or a previous assessment. We see we've got a bridge that's about 5.2 meters wide, 2.4 meters rise, relatively shallow fill, and road surface above it. In this case, although it's a 3-ring arch, there are no signs of delamination, so we're going to assess it as if it's a single arch. And this is the type of results that we'll be getting from Ring. And for a permissible limit state analysis, a good way to visualize the situation is that we're not going to be too concerned about the undue damage in load positions that correspond to a PLS adequacy factor above 1. So these bits that come out blue here, but we are concerned where the value dips below 1, so below this yellow line. So over the quarter spans here, where the adequacy factor is below 1, the bridge has exhausted its primary modes of resistance and instead has started to engage the less reliable secondary modes of resistance, such as soil passive pressures and possibly spandrel wall resistance. The load's starting to mobilize the structure and initialize a failure mechanism where this adequacy factor is below 1. And we know that a bridge can't sustain this behavior over and over without joints opening, closing, moving between locations many hundreds or thousands of times without exhibiting the type of load-induced deterioration that CS454 and C800 are looking for. So in this particular case, depending on the volume of traffic experience, we'd be concerned that the structure will show signs of degradation, as indeed we know it has done with that flattening over the left quarter span. So it's a very quick look at how Ring can help undertake that PLS analysis and how it can be used to determine useful information from that. So a little bit about the workflow aids. I'm conscious time is going on, so I'll try and be quick with these. So first off, we have a command line interface and batch files. So one of the things we can do with Ring is allow results to be obtained rapidly by running the software through the command line without a user interface in it, and just getting the raw output from it on screen or in a log file. This is an example of it here in front of us. Effectively, what we'd be doing is taking Ring and saying, okay, for each of these bridges on the right hand side here, we want to change the vehicle that we're looking at, run that over the bridge and see what the corresponding adequacy factor is going to be. And we can do that very easily using the command line and the batch files. All the commands are outlined in the user manual. So if you're more interested in how that might be useful to you, for instance, if you're taking an unusual load over a particular route and you want to check all the bridges in that particular route, then yeah, they're outlined in the manual. You can have a look at that. The other thing that's quite useful is the ability to put in user-defined vehicles, obviously for situations where your same group of non-standard load vehicles may be encountered. So for instance, if you're taking a wind turbine blade from inshore to the shore or something like that, you can define that in the program and either add it to your own library or export it to file for others to use. And it's a very quick and easy method to be able to do that. So I'll just quickly summarize. So we've seen that CIRIA C800 introduces this permissible limit state approach, and that's the state beyond which long-term load-induced degradation can occur. And CIRIA CS454 allows this CIRIA PLS calculation approach to be used as an alternative to their own factoring the calculated ultimate limit state capacity. Limit State Ring 4 has been specifically designed to simplify that process of assessing bridges to both these codes by including a PLS analysis mode, allowing bridge templates with code-specific partial factors, and having material properties set to change within the software. We have that batch mode to allow very rapid assessment of a population of bridges. And we also have a large database of built-in CS454 loading vehicles. You can learn more about the software from our website, so LimitState.com/ring, and also there's a range of documentation available from that same site. We do have a YouTube channel, which has various different webinars with different applications of the software that you can watch at your own time. A recording of this will be available there in the next few days. And as I mentioned right at the beginning, if you have questions, then you can always send them in to info@LimitState.com and we'll be happy to answer them for you. So I appreciate we're a little over time, but we do maybe I'll stay on and we can answer one or two questions. So if you do have any, then do feel free to put them in the interface and we'll try and get onto them. So we've had one question where is it possible to model abutments as a pier where it's not abutting to soil? So yes, I won't do it in the software because we're running over a little bit, but effectively you can say, okay, here is my abutment. If it's a freestanding end pier, don't consider soil pressures behind it. There's a tick box for that and it will allow you to do that. There's another question, is CMIN built in or should we apply outside? So whilst the software is useful for CS454 and C800 analyses, we don't want it to be tied to them. So it's code agnostic, as we would say. So you do need to include that CMIN factor within the partial factors that you are setting. So if you're looking at the templates, you will see there's an explanation of how that's been built in. So it's been added into one of the existing partial safety factors, so that when you run a ULS analysis, that CMIN factor will be taken into account. If you're running it yourself without a template file, then what you'd be looking at is for the adequacy factor that you're obtaining to be 1.2 or 1.8 or above, in order to ensure that the results were saying that you were okay for that service load behavior analysis. Are there any plans to introduce tangential backing? So yes, I'm aware that it's something that exists. There are methods which I think are explained in some of the support articles online that allow you to be able to introduce backing that's not horizontal. That's either using an extra ring of masonry and changing the properties of it, or by introducing a DXF file geometry in order to specify what the exact shape of the backing is. So it could also have saddle as well as tangential backing, but it's something that we are also looking at in terms of the wizard system as well. How can we take into account the condition factor in CS454 in Ring, or modeling any defects? Again, I won't go into it in detail, but it is touched in some of the other webinars that you can get on YouTube. But the code itself says that if you're able to model defects in terms of geometry and in terms of materials within the analysis method, then you can leave the partial safety factors for that alone. Otherwise, if you're not able to do it, then they suggest partial safety factors that you might want to use for condition and things like that. But LimitState Ring does allow you to introduce things like mortar loss on a localized basis, or change crushing strengths, block self weights, things like that, on a object by object basis. So you can go in, you can make changes that will allow you to model your real life situation as closely as possible. And with that, then you don't need to consider a condition factor as well. You can just leave that to be one. So yeah, we've run over a little bit, so apologies for that. But what I'll do is just wrap up and just say thank you to everybody for joining us. Please do look out for other webinars. So we'll be sending out information about them via email, and also on our LinkedIn channel. So if you aren't already following us, then head on over to LinkedIn and give us a follow, and you'll find out more information about upcoming webinars. And we will send out a recording and a link to our YouTube channel in the next few days, once we have edited and uploaded this video. So finally, just like to say thanks to everybody for joining again today, and do have a great day, and I'll speak to you again soon.